Imagine handing like a billion pixel medical image to the world's smartest artificial intelligence, asking for a diagnosis, and just watching its digital brain instantly crash.
Which is, yeah, that's exactly what happens. It just breaks.
Right. And that is the frustrating reality of modern healthcare right now when it collides with these generic AI
Yeah.
models. I mean, we expect medical diagnosis to be this, pristine binary process.
Oh, definitely. Like a simple yes or no.
Exactly. You break your arm, the x-ray shows a jagged white line and the doctor points to it. But when you step into the world of complex oncology, specifically breast cancer care, you realize you aren't just looking at a single snapshot.
No, not at all. It is the absolute definition of, like, diagnostic muddy waters. Treating cancer is never just a single moment in time.
Yeah, it's a whole journey.
It is. It's an evolving continuum, and it demands this constantly shifting perspective. You're moving from a wide-angle lens all the way down to a microscopic one.
And that is exactly why we are here today. So welcome to the Deep Dive. Our mission today is to explore a truly fascinating leap forward at the intersection of AI and healthcare.
It really is a massive leap.
It is, and we are pulling this entirely from a newly published research paper. This is dated June 4, 2026. Researchers from institutions including Alibaba's Demo Academy and Hupan Lab have introduced a model called BreastGPT.
BreastGPT.
Yeah, and this is an AI designed not just to read, like one type of scan, but to handle the entire messy, real-world clinical workflow of breast cancer care.
Which represents just a monumental shift in the field. I mean, we are finally moving away from artificial intelligence that acts like an idiot savant, brilliant at one tiny, narrow chore.
Right, but useless at everything else.
Exactly. And we're moving toward an AI that actually functions as a comprehensive reasoning engine across multiple stages of a devastating disease.
It's thrilling, honestly, because this isn't merely a medical story. It is a blueprint for how AI will eventually transition into all complex professional workflows.
Oh, absolutely. It's universally applicable.
So whether you're curious about the future of healthcare or you just want to understand how next-generation AI is evolving past that basic chatbot phase, you will want to hear this.
For sure.
But to grasp why BreastGPT is such a disruptor, we really have to understand the specific bottleneck it's breaking through. And if we look at section 1 of the paper, it outlines the core problem with the current landscape of medical AI before we even get into the new tech. It basically says all our current models are entirely siloed.
Yeah, the terminology the paper uses is that existing medical multimodal large language models, or MLLMs, are restricted to single modalities.
Like they only do one thing.
Right. They are trapped in their own specific lanes.
Meaning you have an AI model that is, a world champion at reading a screening mammogram, but if you show it an MRI, it literally has no idea what it's looking at.
It's completely blind to it.
Yeah. But the clinical reality of breast cancer care is a staged continuum. Section 1 breaks this down into 3 distinct phases. So first, you have the screening phase. This utilizes mammography, breast ultrasound, and chest CTs.
And the goal there is just early detection, right? Risk estimation across a broad population.
Exactly. You're casting a very wide net.
The clinical objective at the screening stage is simply to ask, is there anything suspicious happening here at a macro level?
And if a patient actually has a suspicious finding, they get pushed into the diagnosis phase. And here, the paper notes that multimodal MRI becomes the pivotal tool.
Right, because now you need fine-grained characterization.
Yeah, you are trying to evaluate the actual probability of malignancy.
So the clinical question shifts completely. It is no longer just, is there a problem? It becomes, what is the precise anatomical nature and, vascular behavior of this problem?
And finally, you reach treatment planning. This is where the doctors bring in gigapixel whole slide images.
Oh, the WSIs, massive files.
Huge. These are massive, microscopic pathology slides of the actual human tissue. The goal here is to understand the complex cellular biology of the tumor, so they know exactly what drugs or surgeries to use.
It's a completely different scale.
It is. Okay, let's unpack this with an analogy. Our current AI landscape is basically like having a factory assembly line where every worker speaks a completely different language and operates in a soundproof booth.
I love that analogy. That's exactly it.
Right. So the mammogram AI speaks Spanish, the MRI AI speaks Mandarin, and the pathology AI speaks Greek. None of them can read the other's notes. BreastGPT acts like the ultimate bilingual project manager who oversees the entire pipeline.
Understanding every language and carrying that context from station to station, that captures the workflow perfectly.
It really makes you realize how fragmented things are right now.
Yeah, because a clinically useful AI has to do so much more than just circle a bright pixel on a monitor. It has to preserve the specific reasoning style expected at each distinct stage of care.
The actual logic changes.
Completely. The way a radiologist thinks, the vocabulary they use, the logic they apply during a screening mammogram, It's fundamentally different from how a pathologist thinks when scrutinizing a cellular slide.
For treatment planning, yeah.
Right. So the AI must adapt its reasoning dynamically as the patient moves through that pipeline.
But how do you even begin to build a unified brain for something with that many moving parts?
With data. A lot of data.
Right. It requires an absurd amount of training data. And I don't just mean a folder of JPEGs. If we jump to section 3.1 and figure 2 of the paper, we see how they did this before we dive into the data itself. The authors detail the construction of what they call the ultimate medical data engine. They named it BreastStage.
BreastStage is really the bedrock of this entire endeavor. I mean, you cannot train an AI to understand a complex clinical workflow if you don't feed it data that perfectly mirrors that exact workflow.
The scale of this data set is just staggering to me. Section 3.1 reveals that BreastStage contains 1.86 million instruction-following pairs.
It's
It integrates 17 different data sets spanning 5 different imaging modalities. We're talking about 660,000 unique 2D and 3D medical images.
just a phenomenal amount of information.
And then looking at figure 2, it outlines the actual construction pipeline. They didn't just dump all these images into a server. They took raw data from public data sets and partnering hospitals, had it cleaned and annotated by actual breast oncology experts.
Which is incredibly labor-intensive.
Yeah, and then they processed it using an advanced AI called Qwen3 Max to generate the textual and instruction data.
The intentionality behind that pipeline in Figure 2 is what makes it revolutionary. They curated over 130 specific clinical task templates.
Wait, what does a task template actually look like?
So an instruction-following pair is essentially a highly structured question and answer. They are explicitly training the model to answer complex questions, generate full pathology reports, extract specific tumor attributes, and visually ground its findings.
Visually ground, meaning physically pointing to the tumor in the scan.
Exactly, drawing a box around it.
Okay, here is where I have to play devil's advocate and push back a little bit.
Sure, go for it.
Because 1.86 million instruction pairs sounds really impressive on a press release. But anyone who uses AI knows it hallucinates.
Oh, all the time.
Right. It will confidently make things up that sound totally plausible. So if they used another AI model, Qwen3 Max, to generate all the text and instructions for this training data, how do we know this data is actually medically sound?
That's the big fear.
Yeah. How do we know the AI didn't just invent a bunch of fake clinical scenarios to inflate that 1.86 million number?
It is the absolute right question to ask. The medical community is notoriously skeptical of AI for exactly that reason because, a hallucination in oncology could be fatal.
Exactly.
But the researchers anticipated this. They constrained the AI using a very strict methodology in the paper. The data generation is tightly pinned to structured clinical records.
Okay, explain the mechanics of that. How do you pin it down?
Think of a structured clinical record as a rigid spreadsheet. It's filled with undeniable facts provided by a human doctor.
Okay.
So tumor size.
Okay.
2 centimeters. Location. Upper outer quadrant. Grade. 3. The AI, acting as the data generator, is not given a blank document and asked to just invent a story.
It's not writing fiction.
Right. It is fed that rigid schema of verified clinical facts. The underlying language model is only tasked with rewriting those categorical bullet points into fluent clinical descriptions or conversational questions and answers.
Oh, okay, I see. So it's like giving a ghostwriter a strict, chronological, bulleted list of historical facts.
Yeah.
You tell them, Columbus sailed in 1492 with 3 ships.
Yes, exactly.
They can turn that into a beautiful, flowing paragraph about 1492, but they are architecturally locked from adding, and then he fought a dragon.
Right. The AI cannot invent new clinical facts because it is shackled to the human verified schema. The underlying clinical truth remains untouched. It is merely reformatted.
That makes total sense.
And to prove that this worked, they didn't just test BreastGPT on the data it studied. They created something called BreastStage-Bench.
What's that?
It was a held-out benchmark, basically a separate, pristine collection of real-world workflow scenarios kept entirely hidden from the AI during training.
Oh, so like a final exam it couldn't study for?
Exactly. It was developed in tandem with human oncology experts to serve as the absolute gold standard. It measures whether the AI actually learned the complex medicine or if it just lazily memorized its own training data.
Wow. So they have this pristine, massive data set. The next hurdle is actually building the machine that can digest it. Because as we mentioned earlier, throwing a billion-pixel pathology image at a standard AI will literally break it.
It just crashes the system, yeah.
So I want to talk about how they solve this.
Well, this requires looking at Section 4 and Figure 3 of the paper before we really get into how the model works. This is where the engineering brilliantly bridges the gap between the micro and the macro.
Okay, break that down for me.
Yeah. So BreastGPT is built on top of an existing very powerful vision language model called Qwen3VL. But they adapted the architecture specifically for this clinical gauntlet. First, they implemented what they call stage-aware system prompts.
Stage-aware system prompts. What exactly is that doing in the background?
Think of it as a lightweight task router. Depending on where the patient is in the diagnostic continuum, whether that's screening, diagnosis, or treatment, the system prompt dynamically alters the AI's internal behavior.
So it changes its personality almost.
Essentially, yeah, it whispers to the model, you are now acting as a screening radiologist, look for broad anomalies, or you are now a cellular pathologist, scrutinize these specific cellular markers.
That's brilliant.
It is. It allows one unified brain to switch reasoning hats without needing clunky, separate software modules for every single task.
I love that. But the part that completely fascinated me was how it handles the physical images, because a mammogram and a cellular pathology slide are completely different animals when it comes to file size.
Oh, they are on different planets. I mean, a standard radiology scan, like an MRI, is relatively contained. But a whole slide histopathology image, the tissue sample sliced thinly and put on glass for the treatment planning phase, is a gigapixel image.
Gigapixel, meaning 1 billion pixels.
1 billion pixels.
And if you feed 1 billion pixels into a standard large language model,
It crashes. Every AI has a token limit, which is essentially the maximum capacity of its short-term memory. A gigapixel image instantly overflows that memory buffer.
right, so how do they fix it?
Well, Figure 3 illustrates how BreastGPT overcomes this with a dual-branch visual encoder that features a resolution-aware gating mechanism.
Okay, let me try another analogy here. Tell me if this works. Let's hear it. It's like a highly efficient triage nurse at a hospital entrance. When an image arrives, the gating mechanism takes one look at the file size and resolution of the triage part and instantly routes it down one of two completely different hospital corridors.
Yeah, that's spot on.
Standard radiology scans get sent down the standard branch corridor for normal processing. But those massive microscopic slides get routed down the heavy-duty gigapixel branch corridor.
That is exactly how it functions. The triage nurse routes the heavy cases to the specialized trauma bay. Now, what happens inside that gigapixel brand is crucial. The model uses a technique called concept-preserving token compression.
Wait, concept-preserving compression. Break that down for me. How do you compress 1 billion pixels without blurring out the exact cancer cells the doctor is looking for?
Right, because standard image compression just throws away random pixels to make a file smaller.
Which is fine for a selfie.
Yeah, fine for a vacation photo on your phone, but absolutely fatal in oncology, where tossing out a few pixels might mean deleting a malignant tumor.
Wow, yeah.
So concept-preserving compression works by analyzing the clinical meaning of the regions. If the AI sees a massive expanse of normal, uniform, healthy fat tissue, it mathematically groups all of that together and compresses it into just a few data tokens.
Oh, I see. It says, okay, this whole area is just healthy fat. We don't need all the details.
Exactly. But when it detects a complex, chaotic cluster of cells that looks highly suspicious, it allocates a massive amount of its memory budget to preserve that specific region in ultra-high fidelity.
That is so smart.
It really is. It shrinks the overall file size down to fit in the AI's memory, but meticulously guards the crucial clinical concepts.
That is phenomenal.
Mhm.
So what this dual branch system is doing for you, the listener, is basically instantly switching from taking a wide panoramic shot of a mountain range to studying a single grain of sand on that mountain without ever losing focus.
Perfectly said.
Okay, so we have this beautifully designed dual branch system. The real test is what happens when you put it up against the Goliaths of the AI world.
The big guys.
Yeah. And to see that, I want to jump to section 5.3 in tables 1 and 2 of the paper before we look at the overall performance. And I also want to mention table 14 before we discuss the 3D bounding boxes. But starting with those first two tables, the results are wild.
This really is the moment of truth for workflow-aligned modeling. We are comparing a specialized, tailored architecture against models that possess vastly more raw computational horsepower.
And the specialist wins by a knockout.
Yeah.
Based on section 5.3 and tables 1 and 2, BreastGPT absolutely outclasses the general-purpose frontier models. On closed-ended questions where there is a definitive factual medical answer, BreastGPT achieves an incredible 75.66% accuracy.
Which is huge.
And on complex, open-ended reasoning tasks, it scores an 89.92%.
Those figures are exceptional given the density and nuance of oncological reasoning.
It gets even crazier when you look at the competition. The paper pits BreastGPT against GPT 5.4, which is a massive state-of-the-art multi-billion-dollar frontier model.
The biggest of the big.
Yeah, and GPT 5.4 only managed a 54% accuracy on those closed-ended questions.
Ouch.
That is a massive performance gap, and it extends to visual capabilities, too. When you look at Table 14, which evaluates visual grounding, BreastGPT is the only model successfully producing non-trivial 3D bounding boxes in CT and MRI scans.
We'd really need to highlight why visual grounding matters here.
Yeah, please do.
It is not enough for an AI to just spit out a text prompt saying, I detect a tumor in the upper quadrant. A human surgeon needs to know exactly where it is.
They need a map.
Exactly. Visual grounding means the AI is physically drawing a precise three-dimensional box around the exact coordinates of the anomaly within the multi-layered scan.
And the general models just can't do that.
The general models completely fail at this because
I
they
see.
lack the deep spatial awareness required for complex medical imagery.
I have to ask the obvious question here. Why do these massive general AI models that have essentially read the entire internet, can code complex software and
Yeah.
pass the bar exam, why do they fail so spectacularly at this specific task compared to BreastGPT?
It really comes down to how these systems learn to communicate. General web scale pre-training teaches an AI a little bit about everything. It learns the average language of the internet. But breast cancer pair does not use average language. It relies on highly specific, rigid professional dialects. For example, the paper frequently references BI-RADS terminology.
BI-RADS. What does that stand for, and why is it so hard for a general AI to grasp?
BI-RADS stands for Breast Imaging Reporting and Data System. It is a highly specific, standardized lexicon created so radiologists around the world can categorize findings without ambiguity.
So it's a code.
Yeah, it is not conversational at all. A BI-RADS Category 1 means the scan is entirely negative, nothing to see here. A BI-RADS Category 5 means the finding is highly suggestive of malignancy, demanding immediate biopsy.
Got it.
A general model like GPT 5.4 might conceptually understand what a breast is and it might know what cancer is, but it doesn't fluently speak the rigid syntax of BI-RADS. It doesn't inherently grasp the strict conventions of molecular subtyping used by pathologists when they're looking at cell division rates.
So it's the difference between like hiring a brilliantly smart general contractor to perform your heart surgery
Yeah.
versus hiring an actual cardiac surgeon. The contractor has read a lot of books and knows what a heart is, but they have absolutely no idea how to navigate the specific workflow, terminology, and tools of a surgical operating room.
That is the perfect distinction. What Section 5.3 ultimately proves is that for complex, highly regulated professions, you cannot solve the problem simply by throwing more generic internet data at a massive server farm.
Just doesn't work.
No. The only path forward for clinical AI is domain-specific, workflow-aligned modeling. You have to train the intelligence not just on the raw images, but on the very specific professional process that surrounds those images.
BreastGPT is the specialist that has spent thousands of hours in that operating room.
Exactly right.
As we wrap up this deep dive, I want to talk directly to you, the listener, about why this should matter to you. Even if you aren't a medical professional,
Yeah.
even if you never look at a pathology scan in your entire life, BreastGPT serves as the blueprint for the future of work.
It really does. It's a preview of what's coming.
It demonstrates that the most valuable artificial intelligence over the next decade won't be simple chatbots answering isolated questions in a vacuum. The future belongs to unified systems that can walk alongside a human expert through an entire multi-stage professional workflow.
Across any industry, really.
Exactly. Whether you work in law, structural engineering, or logistics, AI is evolving from a basic digital tool into a highly fluent project manager that understands the entire life cycle of a complex problem.
And, witnessing that evolution raises a profoundly important, almost existential question for the future of specialized human professions.
Sure.
If an AI system can soon seamlessly interpret everything from a macro-level radiology scan down to a...
That is the exact paradigm shift we are looking at. Does the human expert move from physically hunting for the jagged white line on the X-ray to simply verifying and signing off that the AI sounded correctly in those diagnostic muddy waters?
It's a huge shift in identity.
It is. BreastGPT isn't just a research paper. It is proof that this shift is happening right now. Something to think about the next time you interact with an AI. Thanks for joining us on this deep dive. We'll see you next time as we keep exploring the edge of what's possible.